One of the big challenges in an optimization problem is that we're usually given a situation where we have to do a lot of work before we get to the function that we just take the derivative, set it equal to 0, and solve. So before we get to that point, we have to set up the function. And that's usually where the challenge is. So let's just practice that scenario. Let's suppose that we are standing here on the sidewalk and that we want to go to the bus stop. We're here on the sidewalk. There's presumably another sidewalk over here where the bus stop is. But in between us and the bus stop is this grassy park. So here's another sidewalk up here. And in between is this grassy park. I even have a green pen just for this scenario. Now, the shortest distance to the bus stop would be to walk directly across the park. That would be the shortest distance. But here's the difficulty. We can travel faster along the sidewalk than we can through the grass in the park. Our speed is higher along the sidewalk than it's going to be through the grass. So we want to get to the bus stop in the shortest time. We want to get to the bus stop in the least amount of time, not the shortest distance. We travel slower on the grass than we do on the sidewalk. Yikes. We travel faster on the sidewalk than we do on the grass. So now I just need to set up two different speeds for you. Let's suppose that you can walk along the sidewalk. When you're on the sidewalk, you can travel at 6 feet per second. 6 feet per second on the sidewalk. But when you're walking through the grass, you can only go 4 feet per second. So we have to decide what the fastest route to the bus stop is. Never mind the fact that we could probably walk to the bus stop before we finish the calculation of the problem. Because this is not about, say, hey, if you ever find yourself in this scenario, here's a quick math trick that you can use to solve the problem in front of you. We just need to set up a problem. So you are here on the sidewalk, and before you're allowed to leave, Professor Leach wants you to figure out what the optimal distance to the optimal time to the bus stop is, given these parameters. So what we want to do is set up a function that represents how fast we can get from where we are to the bus stop. What we're going to do is we're going to walk along the sidewalk for a little while and then go straight to the bus stop. So our path will look something like this. We'll walk along the sidewalk because it's faster, and then maybe we'll cut up to the bus stop. Now, what a good idea might be at this point is to say, what if we just went straight across the grass? What if we went straight across? So what if we have this 600, and down here we have a 2000. This is at a right angle. So maybe we'll just do 4 feet per second across the path. And then maybe I'll just pretend that I didn't completely miss where the tip of that triangle was. And calculate how far this is. So that's going to be the square root. That will be the square root of a 2,000 squared and a 600 squared. Oops, squared. So it's 2,088 feet. And then at 4 feet per second, oops. So we'll take the 2,088, that's our distance, and divide it by the 4 feet per second. That'll take 522 seconds. So we know we can get to the bus stop in 522 seconds. It might be different if we travel all along the 2,000 feet, because we're faster there, and then do 600 feet at 4 feet per second. So what if we did that? What if we took this path of 2,000 feet at 6 feet per second? So we'll take the 2,000 and divide by our speed 6, and that'll be 333 seconds. And then if we did this 600 feet at 4 feet per second. So the 600 divided by 4 is 150. So 333 seconds plus 150, that's going to be 483 seconds. So it's slower to go across the grass because we're only at 4 feet per second on the grass. And even though our distance is much shorter, even though our distance here is 2,600 feet, because we're spending most of those, we're spending 2,000 feet going 50% faster, we actually cut down on the amount of time that we spend. So can we get more efficient? And that's the question for this problem. So what we can do is say that let's travel X feet along the sidewalk and then travel the rest of the way through the grass. And we'll do the similar thing that we did down here. Take the X feet divided by our speed on the sidewalk, and then we'll take our distance on the grass divided by our speed on the grass and add those two things together. So we've got to figure out how far this, what this side is going to be. So if this piece is X, we can call this part, we can draw a right triangle in here and say this is going to be 2,000 minus X. And then this is still 600. So our distance, this distance, will be the square roots of 2,000 minus X squared plus 600 squared Now we've got a distance that we're traveling on the grass and a distance that we're traveling on the sidewalk. So if we walk X feet along the sidewalk, then go across the grass to the bus stop, we will spend X feet at 6 feet per second. That's the amount of time that we'll spend on the sidewalk, plus our distance on the grass, divided by our 4 feet per second. And this will tell us the total amount of time that we spend walking. Any questions? Now we might look at this and say, I don't really like this. I can't really get around the square root of the sum of the squares. But instead of making the 2000x in this messy thing, what if I move the 2000 minus x over here and the x in here? So just set it up slightly differently. It could be that here's my 2000 along the sidewalk. Here's our 600 along the grass. Our path is going to be along the sidewalk for a little while, and then along the grass directly to the bus stop. So instead of calling x the part on the sidewalk, we could call x the part on the grass. And then that would shift the 2000 minus x to be on the sidewalk. That would mean the distance that we spend on the grass will be the square root of x squared plus 600 squared. So now our function of x will be the distance we travel on the sidewalk, 2000 minus x all over 6, plus the time that we spend on the grass, x squared plus 600 squared over 4. So this is just reformulating it. And now maybe there's less going on in this, so we're okay with it. Also, if we distribute this divided by 6, we get 2000 over 6 minus x over 6. When we take the derivative, this 2000 over 6 cancels out. So that might be handy, and something that wouldn't happen in the other problem. Any questions? So there are lots of ways we can formulate that problem, and that's good. We have choice in how we want to formulate the problem. But there's lots of ways we can formulate the problem. That's bad, because now we have to choose. At this point, we have a function in hand, so it's just take the derivative, set it equal to 0, and solve. Any questions? All right. Presumably, this will be somewhere between 483 seconds and 522 seconds. I don't know if we're going to, maybe, actually, no, not presumably. It might be that 483 and 522 are the two ends and it dips somewhere in the middle. Sorry, I misrepresented. I said what I wanted to, I said the wrong thing. Any questions, comments, snide remarks? All right, let's pause the video here and talk about what's next.